I want to welcome everyone to the University of Maryland Extension Solar Webinar Series. Today's topic, we're going to be looking at battery backup. So let me just address then where we're going to go in today's program. We'll start with kind of a basic look at of battery systems. We'll review some information we've touched on in previous sessions. Batteries do have a place in both off-grid and grid-tied systems, so we'll look at that. We'll look at different ways to configure that system. We'll look at some common battery options that are on the market today, and we'll touch on some technical terms that we'll see appear when we get a little later in today's session, looking at the sizing, like how big of a battery do you need to meet those needs. So we'll revisit some of these terminologies, but we're going to start at kind of a basic level here, and I'll try to provide some useful information here up front before we get into the more technical side a bit when we talk about battery sizing. Okay, so again, kind of a recap of what's been looked at in some of our previous sessions. This is a very basic solar photovoltaic system. And that's what I mean. Anytime you see the acronym or abbreviation PV, that means photovoltaic. It's just a fancy word for solar panels. So that's what I'm saying here. This is a very, very rudimentary system, just as a starting point. But here you have two power sources. You have the photovoltaic array, which is the PV panel, the solar panel, and you also have the battery backup. And so that small picture to the bottom right of your screen shows your solar panel on the left in that photograph. There's a controller and a battery there. The battery's sitting on the floor in the middle. And then you have a DC load, which in this case, in this photograph, is a submersible water pump. It's pumping water out of the bucket and it just drains back into the bucket. So this is a very basic system. The reason that you include a battery in a system like this is because at nighttime, your solar panel doesn't produce electricity. If you have really heavy cloud cover or stormy conditions, that battery is providing power during those times. So you charge the battery up from the solar panel and you have it for any time that you're not producing solar electricity. Okay. The charge controller in the center of that diagram is just the brains of the operation. It protects the battery from being damaged from charging too quickly or overcharging. So anytime you have a battery, you'll also have a control system, a charge controller in place. And we'll talk more about that a bit later in the program today. Okay, here's another example of how you might integrate a system. This time we are using an inverter. So the only difference here is we've added an inverter. If you recall, the function of an inverter is to take that DC power, that's direct current, and convert that into alternating current. And that's relevant because most of us are going to be working with alternating current. Very few of us are running a lot of DC loads. AC loads or alternating current is like the outlet in your house when you plug in a device on the outlet in the wall. That's alternating current. Being that we're mostly working with AC loads, and that could be a TV, a refrigerator, a lamp, anything you're plugging into the wall is AC power. We also need that inverter. It takes the DC power either from the solar panel or the battery, turns it into alternating current that's more usable for the majority of our applications. So this is another example of battery integrated systems. Here's a more traditional solar electric system that's tied to the electric power grid, but it also has a battery. So in this case, you actually have three power sources. You have your solar panel, just like you had before. You have your battery storage, and your third power source is the electric utility grid, the power lines that run down the road. So you can still purchase electricity as normal in this instance. So three power sources gives you a little bit more resilience. The other thing I'll point out here is that we've added a sub panel. Okay, so there's both a sub panel and a main panel. What I mean by main panel, your main service panel, is the circuit breaker panel typically installed in your garage. So that's the thing that whenever you flip a circuit, you blow a circuit because you have too many devices plugged in. You'll go out to the garage, you'll flip that circuit and reactivate that. so that you have electricity running to the outlet again. So that's your main service panel. But typically when you have a battery integrated solar system, you add a sub panel in there. So there's a little added cost with some additional features like that. But with the sub panel, you're providing electricity only to a few key devices. Because batteries are very expensive, and we'll address this kind of at the end of today's program, the cost of batteries is relatively high. You're not going to be able to power everything that you want. Um, so you typically identify a few key components of the system, and you're running those outlets on this critical load sub panel. And so we'll touch on more details of this, but you will have that additional sub panel that's only running a few circuits in the house. Okay, so here's kind of a flow chart of a typical solar photovoltaic system. This is without battery integration, and I just want to highlight again something I've mentioned previously, but the importance of battery and the reasons why we integrate batteries, or why you might want to integrate a battery into a solar system is because in this case, without the battery, your solar panels are producing electricity. It goes obviously through the inverter to become a more practical form of power of alternating current. From there, it goes into the main breaker box there in the center of your page that you can see there. The main breaker box distributes that electricity to all the rooms of your house. You can run any load that you want, light bulbs, TVs, refrigerators, and all that. It can also, if you produce extra electricity, that'll go through your meter and out onto the power grid with net metering in Maryland. Any extra energy that you generate goes onto the grid, and vice versa. If you're not producing enough solar power, you're purchasing that energy from the grid, so the meter goes both ways. But in the case that there's any damage to the power lines from a storm or something, you will be left without power, because by design of the system, the inverter is designed and regulated. It's mandated to be turned off during that event. So if there was damage somewhere down the road from you to the power lines, your inverter for your solar electric system will be deactivated, and that energy will be stuck at the solar panels. It's not going to be accessible to you. So when we integrate a battery into it, and unfortunately, I think I pulled some of that information from the curriculum. You can go on and if you download that yourself, you can see some additional examples of that. But when you integrate the battery into into this diagram, what happens is that you're creating essentially a microgrid, where you're powering those critical devices. Again, not everything with batteries, but your critical loads. And so you isolate the system. You have a standalone isolated system that's not attached to the grid. And the reason why this is that if you're producing solar electricity, it would be dangerous for it to be any of that solar electricity to be sent onto the power lines. If they send repair crews out there to work on that system, that would pose a risk for them. So by law, that shuts off. So that's why batteries are integrated. You can have a standalone isolated system and still power those devices that you want to power. There are several different ways to install a system. These are obviously oversimplifications, but I'll share kind of two broad categories of installation. One is called AC coupled systems. That's what's shown on the top. So with an AC coupled system, this is most prevalent with existing solar arrays. So if you already have a solar electric system installed, you may not want to go back and pull that system apart. And if sometime down the line you want to install a battery-based system in there, many people will choose to install a separate isolated battery system. So you look at this figure on the top for AC coupled systems, you have your solar panel, solar array, and it has its solar inverter to make alternating current. You also, on the right-hand side of that picture, you have a battery system, and it has a battery inverter to make alternating current. So you have two standalone systems. You haven't had to change anything that was existing with that previous solar array that you had installed. So that's an AC coupled configuration. On the bottom is that DC coupled system, and you'll see this more likely with when you're installing solar and batteries at the same time. Okay, and there's many different ways you can do this, but this again, this is an oversimplification. But in the bottom diagram, it's a more streamlined flow where you have solar panels on the left going through a charge controller to regulate to the battery. The battery then goes to the inverter, and then you just have that one inverter making alternating current. Okay, so that's a DC coupled system. Just be aware that there's different ways to build the system out based on where you are in the process. I will touch on a few kind of common technologies out there. Everything from the lead acid batteries, you have flooded, AGM, and gel. Those are your more traditional technologies. Lithium ion is much more prevalent today in many applications, electric vehicles and different battery packs or lithium-based batteries. But I think there's other technologies we could probably talk about, but I've just kind of limited the discussion to these kind of common systems out there. The flooded lead acid is kind of on the lower end of the cost spectrum typically. There's a little bit of maintenance involved with the flooded batteries because they have electrolyte fluids in them that have to be balanced. AGM and gel or other more traditional technologies, there's less maintenance with those. But the one thing I do want to point out when you're looking at newer lithium-based technologies, they do have a higher price tag typically when you're looking at similar sized batteries. But the benefit with lithium-based batteries is typically a much greater lifespan. This particular battery, I think, was warranted for 15 years, so you can expect a lifetime at least for that. You also have a greater number of cycles with the lithium-based batteries. A cycle refers to every time you use all the energy in the battery and then recharge it. Okay, that's how batteries are designed. Is you use the energy up and then you recharge the battery. That's a full cycle. Just like your phone works. So you use your phone all day long. At the end of the day, you have to plug it in and recharge it. That's a cycle. You get a lot more cycles out of lithium ion batteries. Of course, it's manufacturer and model specific, but in general, you get a lot more cycles out of that. And we'll talk about some of the trade-offs here when we start talking about battery sizing and system design. I'll say just briefly, take a look at some of the terminology that will appear later and things that we need to take into account when we're picking the right size battery. This term depth of discharge, you'll hear me refer to it several times throughout today's program. And what this kind of entails is how deeply you can reach into the battery or dip into the battery's capacity. When you're looking at a battery, it'll have a nameplate capacity written on it. But just recognize that not all of that energy is available. You can only take a certain amount of the battery out before it is damaged irreparably or severely or significantly could impair the longevity, the lifespan, and the number of cycles that you get out of a battery. So for the example, lead acid, and maybe this particular slide says 30 to 40, maybe you'd be closer to 50% with your modern lead acid batteries. But with a lead acid battery, you're only getting, at most 50% of its available capacity. If you dip in deeper into that capacity and use more of that capacity, if you go up to 60 or 70%, you're going to damage the battery and shorten its lifespan. So just know that you have to kind of upsize the battery capacity, knowing that you're not going to have 100% of its energy available to you. Lithium ion gives you, again, there's a cost difference. Lithium's more expensive battery, but you're able to access a bit more of that energy as well, 80 to 90% or more of the capacity before you do any damage to the battery. Again, that's model specific and you need to look at the specifications for that particular battery. But that's a general consensus there. To demonstrate that, there's a couple graphs here. I don't remember exactly which battery type this was, but let's take a look at the graph on the right. I think that's helpful. So this is a graph of the number of cycles on the up and down, and then you have depth of discharge across the bottom. So at 100% here at the end of this curve, 100%, what you have is if you're using 100% of that battery capacity and you're dipping as deep as you can go into the battery, you're only going to get 1,000 cycles out of this particular battery. Okay. If you are only going to 50%, if you only go to 50% of its depth of discharge, which would be more common with what you do with a lead acid battery, in this particular example, you'd get over 3,000 cycles. Okay. So again, trying to demonstrate the fact that not 100% of the energy is available. You could get 100%, but you'd be damaging and shortening the lifespan of that battery. So you don't go as low as you can. You only go to a certain percentage. Another piece of information I want to point out is what's known as the days of autonomy. This factor, as well as what I just talked about with the discharge, these all appear when we look at how to size a battery. And typically you're designing for how many days you think you can go before you need to recharge the battery. Okay. No matter how many days you pick, eventually you will run out of power in the battery if you're not recharging it. So if the power is down and you don't have electricity from your power company, you can't charge your battery. If you're not producing solar power, then it can't charge your battery. So what days of autonomy does is you're assessing how many days do you expect to be unable to charge the batteries. So if you wanted to be very resilient, you'd obviously pick a greater number of days. If you wanted to go a full week and say, conditions might be really bad. There's a hurricane, something like that, and you're not going to be able to charge your battery for some time. You might design it for 5 days of autonomy. That would be pretty expensive though, because it would require a lot more batteries. Batteries are expensive, and if you design it for a really big a number of days of autonomy, that's going to cost you. Now, there's a benefit there because you have a lot of batteries that each one is protected and preserved a little bit better. If you have, 100 batteries, then each one is only dipped into a little bit, and they're going to last, each one of those is going to last a lot longer, but that's very expensive. On the other hand, if you only pick 1 day of autonomy and you're really hopeful to be able to have your system up and running and charge the battery again, 1 day of autonomy is not very much. And as a result, you'll probably dip deeper into that one battery or however many batteries it is. If you've only designed around 1 day of autonomy, there's a trade-off there, is that you're going to have fewer batteries and you'll probably be using those fewer batteries at a greater level. And so they'll have a little bit more wear and tear because it's not distributed across a big number of batteries. So a conservative estimate, most folks use like 3 days of autonomy. Again, it's a case-by-case basis, thinking about, grid outages in your area and that kind of thing. But a 3 days of autonomy, typically what people do is kind of a balance between more conservative and a different trade-off there in how they might design the system. But we'll come back to this topic of days of autonomy. So here's our next bit that we'll get into in today's session. We're going to talk about picking the correct size battery. So we're going to start by identifying that critical loads, all those essential devices that we want to run. Again, we're not going to be able to run every electrical appliance or device in our house. We're only going to be able to run a few critical loads. So we'll go through how we create an inventory for that. We'll look at battery sizing in terms of the voltage and amp hours. We'll do the same with the charge controllers, and we'll size those. So there's a bit of mathematics involved in this. And let me just preface this bit of the presentation by saying it's not my intent for everyone to pull out a calculator and run these numbers themselves, but I'm going to point out some kind of trends and information that I think is helpful for you to make informed decisions. And if you're talking to a system designer or an installer, you'll at least have some information and say, hey, but what about days of autonomy? Or, what about, the depth of discharge in the batteries? So, you'll have some information there. So we're not going to get too caught up on the mathematics of it, but I will point out some as we kind of go through. Okay. So the first thing I'll point out here is when we look at an electrical appliance, we're going to be interested in one thing up front is the power rating. For this coffee maker, it's 900 watts. And so, again, what we're aiming to do here is to build out a loads inventory of all the loads that we want to run. So, let's say our coffee maker in this case is identified as a critical load. You can't live without your coffee during that power outage. And so if you wanted to power this with batteries, you'd look at the back of the coffee maker or the owner's manual and you'd see what the power rating is. This is something we've talked about in previous sessions, so I'm not going to spend as much time on it today. If you really want more information, you can go back and review some of those earlier sessions. But you're going to look at the power rating for the coffee maker. If that's not available, there's other ways to calculate that. But 900 watts is the rating for this coffee maker. So you need the instantaneous power for that. You have to reach that 900 watts. But we're going to be interested in some other aspects as well. And I'll just kind of briefly recap how we've done this in the past here in a minute. So power is one thing. That's an instantaneous power level that we have to hit. Some devices have a really high surge power rating, and especially any heating systems or other pieces of equipment might have a high power rating. So you have to be able to have that surge power. But the other aspect we're interested in is the energy, which takes place over time. So, I said this before, but power is like the amount of water in a garden hose or the amount of electricity in a wire. That can change, from 1 minute to the next, but this is an instantaneous power rating that you need to provide. Energy is over time, and it depends on how long that device runs. So our coffee maker, I think, was 900 watts. That's the power rating. So we need that to meet that instantaneous power requirement, but we also have to account for how long it runs. Now, a coffee maker maybe runs at most an hour in the morning. So it's 900 watts times an hour is 900 watt hours. The light bulb example that I'm showing here in the bottom right-hand corner, it has an instantaneous power of 100 watts. If you run the light bulb for 3 hours, then that's 300 watt hours. So that's how much energy you provide over time. And it really depends on how long you run the device. And so the longer you run it, the more energy you'll need to provide. And eventually, again, you're going to run out of your battery capacity if it runs long enough. So we'll kind of balance those two aspects there. I've shared these examples previously. I'm not going to go through those, but these are just additional examples of how you build that inventory out. You look at every critical load that you want to run. They all have power ratings, and you calculate the energy. kWh is energy, kilowatt hours. And that's what I've done for these examples. Again, I'm not going to go over that again in today's session. We've done that previously. I will just share kind of what you do with that information. Okay, this is a copy of the template we have available on our University of Maryland Extension webpage. It's part of our fact sheet that was put out a few years ago. You can use any other reputable source, whatever is useful for you. You could use a spreadsheet on your computer. But the idea is to build out your list of critical loads. That's going to be anything that you don't want to live without. So you want to keep your refrigerator running so the food doesn't spoil. You'll need a few lights. Medical equipment, of course, you'd want to keep that running. You're not going to run things like heating systems or electric dryers. You're going to have to do without your laundry. And the reason I say that is that, any of those kind of inner heating systems, electric heaters and things like that, water heaters for hot water, those have a really high surge power. It has a really high energy use. So you don't want to try to design a battery system that can provide heating systems like that. They're very energy intensive. So we typically stray away from that. It's not saying it can't be done, but it would be very cost prohibitive. You'd be better off looking at diesel generators or other sources of energy for that. So again, you identify the critical loads. You'll put what the power rating is. I know you can't see all the details in this particular snapshot, but you'll put all the details in there, the power rating for each device, and you'll run through and it'll calculate the energy for you. Okay. Um, so that's how you build that out. Now, the first thing we'll look at is picking the correct voltage for your battery based on that information. So, if you're doing a DC system or a simple kind of off-grid system, it's pretty easy. You're going to pick the voltage battery that matches whatever the load is. So again, I don't think many of us are working with DC power systems, but if you have like a DC pump or something, just just pick the right voltage that matches that pump. So if it's like a 24 volt pump, which is common on boats, you'd pick a 24 volt battery. If you have a 12 volt light, use a 12 volt battery. Those are nameplate nominal ratings. They will operate a little bit different than that depending on how much they're charged. But in general, you're going to use that 12 volt, your match 12 volt battery with a 12 volt load. 24 volt with 24 volt. If you have an inverter in your system, look at the specifications for the inverter. Smaller inverter, like 2,000 watt inverter, kind of on a smaller range, will typically use a smaller battery. It'll require a smaller DC input. And so you might be at a smaller inverter, you might be using a smaller battery, like a 24 volt battery. A larger inverter, like 6,000 watts, will probably be 48 volts. But again, you'll have to look at the inverter specification and see what the DC input is expected to be and pair it. So you're either pairing it with the load or you're pairing it with the inverter size. The other thing I'll point out, and this goes back to the question I posed earlier about why you might pick a larger voltage. So if you do end up having a choice to pick a larger voltage, that will benefit. You might pay a little bit more for the battery if it's a higher voltage rating. It just depends. You might buy more batteries. But if you do pick higher voltage, it will help you to reduce the size of your wiring. The gauge, the wire gauge size can be smaller with a higher voltage. I won't get into too much of the electrical aspect of that, but again, it's because the current is higher, you can downsize your wire. And that's important if you have a really long stretch of wire. You can save a lot on a long stretch. Now, you typically want to avoid those long wire runs. You'll put your battery in a more strategic proximity to the rest of the system. But if you have to, that's a way to cut back on some of the wiring costs. The other thing I'll point out, you see a number of different configurations for batteries that can be wired together in any number of ways to get different parameters. So I think maybe I'll just point out in the bottom here, there's a row at the bottom here of batteries. So these are 12 volt batteries, and there's 4 of them connected in series. So if each one of these is 12 volts, it's 12, 24, 36, 48 volts total. So if you're doing a 48 volt system, you can get 4 12 volt batteries. So there's different ways you can piece those together. Just be aware of that. So that's the first thing, is you're kind of looking at the nameplate voltage rating and pairing that to the inverter or the load. The other thing, and this is a lot of math here, and like I said, I'm not going to run through the calculation here, but I do want to point out some of the key factors here that if you do want to revisit this later, you'll know what's involved. And so I'm going to touch on some of those aspects. Now, I just talked about the voltage rating, and every battery has a voltage rating, but every battery also has an amp hour rating. Amp hour is abbreviated AH, and so that's what's done in step 2 is calculated the amp hour capacity. So you want to check the voltage for your system, make sure your battery is the correct voltage. You also want to check the correct amp hour capacity, AH capacity. You'll see both of those numbers on every battery. And so I'll just quickly touch on a few key aspects. We're not going to do the math itself. But step one, or rather step zero, I started with step zero, and this is because it's kind of a reiteration of our load inventory. So I shared that spreadsheet a little bit earlier, all the critical loads listed, all the energy. That's just a kind of a recap of this information. The only new thing that's in step zero is I've included this inverter efficiency rating. And the reason we do this is that the inverter is not 100% efficient. You actually have some loss of energy through that system. And so as you go from DC power to AC power, you'll lose. I typically say around 8%. So that's why I've said 92%. I've included this factor 92. Again, I don't want to get too bogged down in the mathematics of it. If you are interested and want to follow up with me on this, I'd be more than happy to provide additional information. But the concept here that I want to portray or convey is just that when you go from AC power to DC power, you're losing a bit of that energy. That means you have to upsize the system a little bit in order to, because we're talking about how much AC power we need. Well, how much DC power we need is actually a little bit more. So we have to upsize that a bit. That's what's done in step zero. Step one, we're looking at the overall tank size, what I call the tank size or watt hours for the battery bank. Okay. Regardless of how many batteries you need, this is the entire size of your battery bank. It's based on whatever our daily use was. That was just done up above in step zero. So we have our daily use. But I want to point out a few other terms that appear here. Days of autonomy. Again, that is how many days you can go before you have to recharge your batteries. So if you picked, you're going to make it a whole week and you have really bad conditions and you're going to try to survive a whole week with your batteries, you'd say 7 days there. That would increase the overall tank size for your system. So you'd need a lot more battery capacity overall if you're going 7 days of autonomy. I've picked a more conservative 3 days of autonomy for this example. A temperature multiplier, and again, just pay attention to the concepts here, but a temperature multiplier is because batteries work on under different conditions, temperature conditions. So most batteries are rated under, a standard test condition, 77 degrees. But if you install your battery in the garage where it's a little bit colder this time of year, it's not going to perform as well. And so you're going to impair the capacity of that. So that would be another factor why you might have to upsize the battery to make sure it still provides enough power even in the winter. I'll share some information on that temperature factor, I think, in a little bit later. The last factor is, again, that discharge, the depth of discharge. So again, you cannot use 100% every bit of energy that's in each battery. So I put a value of 50%. That's there on the bottom, 0.5. That's for the more traditional lead acid battery. If you're using a lithium battery, you go to 80 or 90% there. But again, this is a way of upsizing the system, knowing that you can't actually get all of the energy that's in the battery. So those are some of the factors in step one to determine the overall battery size that you need. Okay, regardless of how many batteries you end up buying, that's the overall tank size that you need. Step two is where you actually calculate this important value of amp hours. Okay, so again, we looked at voltage, picking the correct voltage. Now we're going to determine the amp hours or AH. So step two, we're just looking at the overall capacity of the bank. We're dividing it by whatever system voltage we picked. For this example, I said 48 volts. That might be because you have a large inverter that requires 48 volts. Maybe you're trying to design with smaller wiring. So you've picked a high voltage like 48 volts. Whatever the reason is, it's 48 volts. And for my particular design, just as I've kind of illustrated on the far right, bottom right here, I designed this battery system with 2 strings of batteries. Again, you can wire these in series with one another and increase the voltage. So these are small 6-volt batteries. I wire a bunch of those together. So the string number 1 there's a bunch of 6-volt batteries in string number one. That adds up to 48 volts. String two also adds up to 48 volts. So that's how I designed this particular system. That factors into how many strings factors in here. So each of these strings is 177 amp hours. Um, each battery is 177 amp hours. So that's how I would check when I'm at the store. I check the voltage. 6 volts will work if I connect it in series, and 190 amp hours for this particular battery. That is more than enough for my, even in the winter, I'll have more than enough. So the amp hour capacity is good. So that's kind of a basic overview. Step 3 and 4 is just kind of how the system was set up in terms of how many batteries in a row and that kind of thing. I won't go into the detail there. I will say you don't want to have more than 2 strings. The imbalance in the charging can get out of hand there. So you typically will only have 1 string of batteries or 2 strings at most before you start to run into problems. But that's a general census. So again, just kind of a recap with batteries, you're looking at the voltage and you're looking at the amp hour capacity. Okay. Um, I know that's a lot of information. If there's questions, please send those in the Q&A and I'll look at those in a minute. Related to the temperature factor here, we've got, again, kind of looking at the impact that colder temperatures has on battery capacity. This particular battery, and this is given in the owner's manual for the battery and the specification label for it. In this particular battery at like 80 degrees Fahrenheit, it has 100% of its capacity. Okay. So 100% of the capacity is available there. But if you, again, install the battery like in your garage, you're at maybe 50 degrees out there, then your capacity drops to maybe, what is that, like 82, 83% capacity. So those colder temperatures do impair the function of the battery. You have to compensate for that. So going back to those calculations I just ran through, this type of information was included, that I looked at a 50-degree temperature and I included this temperature multiplier. This is all available in the battery specifications for that particular battery. Okay. So we talked about batteries. We'll switch and talk just a minute here or two about the solar charge controller. Again, the charge controller is what is the brains of the operation between the solar panel and battery. It regulates the flow of electricity to and from the battery. It'll actually go through a number of different charging phases. I won't really get into that today. It depends on the chemistry of the battery and a number of control parameters in place. But the idea is, initially, if the battery is really low, it'll charge quickly and it'll be recharged very, very quickly with a high energy flow. If the battery is getting more towards its filled position, it'll taper off and do more like a trickle charge phase. But there's that control system in place there. Excuse me. A lot of controllers these days have a connection for DC loads. Most of us probably won't use that direct connection, but you could run directly off the panel or battery with that connection. But that's the function of the charge controller. Okay. Now I talked about matching the voltage of the battery to your system. You also match the voltage of the controller to your system. And especially with older style charge controllers, it was really important to match all the voltages in the system. So you'd want the voltage of your solar panel to match the voltage of your battery. And then obviously you'd match the controller as well. So there's a 12-volt system. It's 12 volts at the panel, 12 volt at the battery, 12 volt at the controller. Same thing on the right-hand side. Here you have 2 panels. So you have 24 volts for the solar. You have 24 volts for the battery, and you'd pick a 24 volt charge controller. And that's, again, especially true with the older style systems. Now, unfortunately, this is not real life conditions. Your panel is not exactly at 12 volts. It's very condition specific at what voltage is actually being produced. So you do have to do a little bit more legwork beyond just kind of this nameplate rating. But this is a good place to start to kind of pick the right category of these nominal voltages. To get a true assessment, you'll look at the worst case scenario, again, because a solar panel can produce more voltage than its nameplate rating. So trying to give the example here, if three solar panels were connected in series, these all have a nameplate rating written on them as 20 volts. So you have three panels, that's 20, 20, 20, that's 60 volts total for for those three solar panels. 60 volts is the total. Now, if you're looking at a charge controller like this black model here on the left, the model number for this particular one is 150 MPPT. Right there in the model number, it tells you it's 150 volts. So just referencing the nameplate rating for these solar panels, 20, 20, and 20, it looks like your 60 volts is well within the maximum threshold for this charge controller. Unfortunately, again, it's more complicated than that. Your solar panels can produce more voltage and more likely will produce more voltage under different situations than 20 volts each. So we will estimate this using the highest possible voltage that can come from each solar panel. This information is on the back of the solar panel. I think I have a picture of a label, but if you look at the back of a solar panel, any solar panel, it'll give you all of these voltage and current ratings. But you're going to look at the highest possible voltage that you can get from that solar panel. It's 38 volts in this example. You have three of those solar panels. And then we also, again, because solar panels work different under different temperature, you'll have to account for your cold weather temperature. Now, I picked the temperature of, I think, -5 to -13 degrees. That's, hopefully we don't see that temperature this year here in Maryland, but in rare occasions we might. But colder temperatures, you'll actually produce even more voltage. So the point here was I was being very conservative and estimating this. So the maximum voltage from the back of the solar panel is 38 volts, three solar panels, and we corrected the temperature to say in the winter we'll get even more voltage. This is 136 volts for those three solar panels. We're still within the acceptable range for this 150 MPPT controller. Okay, we're still below that threshold. If we connected four solar panels, we'd be over that limit under certain circumstances, not all the time. But if you exceed that rating on the charge controller, you go above 150 volts on the charge controller, you could damage it or have a safety issue there. So voltage is one thing, but also just like with batteries, it's not only a voltage issue, but it's also current related or amperage related. So here's two different controllers. The older technology that I'm looking at here on the left is PWM, pulse width modulated. These are not as common, but you can still buy those anywhere. I have a number of them that I work with. PWM on the left, how this works is the controller here in the middle, it takes whatever current is given to it. So the solar panel is operating at a amperage of 11.1 in this case. All 11.1 of that amperage gets passed through the controller and to the battery. So you're still at, on the battery side, 11.1 amperage. Okay, so all the current gets passed through. Now the downside of this is that the voltage still has to be dropped to a range that's closer to the battery voltage. You're typically right above the voltage of the battery, so you still have pressure to charge the battery. It's 13 volts. But you're dropping from a panel voltage of 18 volts to 13 volts at the battery. And so you're chopping off that extra voltage as it goes through the controller. As a result, you lose a significant portion of your power. So the solar panel is a 200-watt solar panel, not necessarily a very large solar panel for this example, but a 200-watt panel nonetheless. And because that voltage is chopped off, we've dropped to 144 watts. So we've lost, and these older style charge controllers like the PWM, you lose that percentage of your voltage and power. That's an unfortunate loss. Now, if you're getting the new modern technology is this MPPT, it's a maximum power point tracking. But this actually is able to increase the current as it goes through the charge controller. So this is a better technology in many ways because the voltage, in this case, I picked a really high voltage at the solar panel, 36 volts, it drops to 13 for the battery. So although you had that voltage drop, the MPPT controller actually boosts that current, and you're going from 5.5 amperage up to almost 3 times that, 15.4 amperage. So as a result, the MPPT controller actually preserves the majority of that power. It's a 200 watt panel and 200 watts of the battery as well. So you're not losing system power there. So that's some of the advantage of an MPPT. As a result of those different ways they work, your assessment of the current rating is a little bit different. So you have to kind of look at what kind of controller you have and how you assess that. I'll quickly just touch on how a PWM is done. You find the current rating on the back of the solar panel. So here's what one of those labels looks like on the back of a solar panel. So you have a number of values. I mentioned this VOC, the voltage open current, a little bit earlier when we looked at the voltage rating. The value I've highlighted in blue here is the short circuit current. So the electrical current measured in amperage, that's 8.68 for each solar panel. For this top example, there's just one string of solar panels. There's only two of them, but there's one string of solar panels. It goes through the charge controller, and we increase the current by what's known as the NEC safety factor. This is a national electric code. For safety issues, you upsize the current because solar panels can produce actually a more electrical current under different circumstances. If there's more sunlight reflecting onto the panel and you're actually producing a little bit more than its nameplate rating, you have the safety factor that's included because the panel can actually produce more power. Long story short, you assess the amperage that's coming from the solar panel. So in the first example here, it's 10.85 amperage. So we'd pick a 15 amp charge controller. That would be enough to handle that from the solar panels. And I won't go through each of these, but if you had two strings, like in the second example, you had two on the top and two on the bottom, so that's two strings, then it would just double your current and you'd have to pick a 30 amp charge controller. So just make sure that the current is big enough. So just like we did for batteries, we made sure the voltage was sufficient. We made sure the amp hours was sufficient. Now we're checking with the controller, is the voltage sufficient? Is the amperage sufficient? Okay, and so that's how you do it for PWM. Again, the more modern technology, MPPT, you're more concerned with the battery side of the system. Again, this is important because with the modern MPPT technology, those controllers actually boost the amperage up on the battery side. So you're more concerned with the battery side, which has the higher amperage on the battery side. So that's why we're looking at the battery side in this case. Again, for this example, we have 3 solar panels in series. Just got this one string of solar panels. It's 240 watts times 3. That's 720 watts total. Divide that by our system size. It's 12 volts on the battery side. So 720 divided by 12. That tells us that we have 60 amps on the battery side of the system. We look at the specification for any particular charge controller. For this one, it has a rating of 60 amps. So we're right at that threshold. 60 amps is cutting it close, but that's sufficient. Okay. So that's how you would look at that. So again, I know there's a lot of math involved in that, but hopefully kind of conveyed some basic principles there. All right, so here's what we're going to kind of wrap up on this last bit of the conversation and presentation. We're going to look at the cost for systems, some of the incentives in place, and then some of the value-added benefits like demand-side management. We'll look at other cost savings that are associated with this. So quickly, I'll just kind of give you a snapshot of the cost for battery systems. It does drive the cost for a solar integrated system up. Just for a frame of reference, it might be useful to look at some of the popular models there in the bottom right chart. Tesla Powerwall. These are lithium-based batteries. It's easily going to be over $10,000, for just one system. And so there is a heavy price tag associated with these. You could save a little bit money on more of your traditional lead acid based AGM systems, but most of the popular technologies, you're talking about a big chunk of money towards that. But again, it's highly variable. It depends on the system design and a number of factors. Hardware cost are the bulk of it, but there's some installation costs as well. That's kind of just in a ballpark what that might cost you. And for scale, that's about, you're looking on average, 10 or more kilowatt hours in capacity for those whole house residential systems. Okay, the federal tax credit used to be one of the major incentives, but that ended on December 31st last year. So that's no longer available for residential installations. I'm not a tax expert, but it is still available for commercial applications. If you're a commercial customer, you can, or enterprise, you can apply for this tax credit with certain stipulations. It has to be tied to a net zero greenhouse gas emission system like solar or wind. It has to be from a certain country manufacturer. There's limitations on that type of thing. So, it's not available for residential anymore, but if you're a commercial enterprise, you could still potentially take advantage of that. Great place is also to look at Maryland Energy Administration. For those of you here in Maryland, they facilitate a number of different grants that change each fiscal year. A couple current ones you might be interested in is the Maryland Solar Access Program. There's also residential and commercial energy storage grants available. Some of these grants and programs are tied to solar. Some are more towards energy storage broadly. But those are some options. The Maryland Energy Administration, you can go to their website, energy.maryland.gov, and get additional information on current grants they offer through the state. So those are kind of the upfront costs associated with it, but I'll say there is some value added benefit to it in terms of load shifting and peak shaving. These are two kind of similar ideas, and I don't mean load shifting in kind of the truest sense of using energy at different times of the day. This is more like shifting your grid demand to different times. And so what I mean by load shifting here is if you're on time of use charge, and that's becoming more common even in residential systems here in Maryland. If you have time of use rates, you're being charged a different amount of energy different times of the day, then you'll use that battery in those different periods of expensive rates and use the battery instead of the grid during those times. And so there's some load shifting you can do there. Peak shaving as well. If you're a commercial customer with your power company, you might be charged a demand charge. And what you want to do here is bring that peak period down with your batteries. And so you have a demand charge based on whatever your highest demand is for that month. And so if you have that charge, you probably want to reduce it with batteries. And there's a number of other things you can do, but with batteries in particular, you can reduce that overall peak so you're not penalized as heavily. I think the last thing I'll say is just on utility outage. I won't go through this data necessarily, but consider on a case-by-case basis if you're dealing with power outages. It's not only an inconvenience for many, but it also for commercial businesses can have a cost associated with that downtime. What I'll share is just kind of average regional values for the cost. And again, this is business by business, what it might cost you. But beyond the inconvenience of it, any downtime will stop your operation from being productive. And so, for agriculture, on average, it'd be over $1,000 per outage. So those are some other value incentives that you might want to consider in the long term as you build out your resilience. Beyond just the inconvenience of it, you're avoiding that downtime in your operation. At least you can keep part of your system up and running. So those are some of the value-added benefits. Now, as I get kind of close to closing here, I'll just point out some of the resources that are used and referenced in this presentation. Here's kind of a recap of where you can find this curriculum and educational resources related to solar and batteries at our extension webpage, extension.umd.edu/energy.